All right, so we're wrapping up the final practice exam with number 44 through to the end. In number 44, we're looking for the relationship between potential difference and current in terms of a graphical representation. We have a copper wire at a constant temperature. Now, that's also a clue. Constant temperature, or the fact that it's mentioning constant temperature means that we're holding the resistance constant. You can tell that because on the tables for electricity, we have resistivity values for wires at constant temperature of 20 degrees Celsius. Now, that resistivity value is not resistance. It's related to the resistance of the wire, also alongside length of the wire and cross-sectional area. But because it's a factor that we're holding constant, it's kind of a clue that resistance is involved here, because that is what this question is addressing. Potential difference is voltage. Current is, well, I. So essentially these graph axes say V and I. The relationship between V and I is R, resistance. This is Ohm's law, right here. So the slope of these graphs should be resistance. V on the y-axis, I on the x-axis. That would be an increasing graph. There's nothing squared related or exponentially related with voltage, current, and resistance. If voltage increases, current increases. And once again, the Ohm's law equation says that. If you increase V, you have to increase I so that R remains the same with constant temperature. Number 45, again, we're addressing the resistance of a wire at a constant temperature. So we see yet again the clue, temperature constant, we're dealing with resistance. It's tungsten, so we can go and look at the resistivity value. That's this Greek letter rho. For tungsten, it's this value. We would multiply that by the length of the wire and divide out the cross-sectional area. Now we're told that we have a wire with all the variables as normal, and then a second wire where the length is doubled and the cross-sectional area is halved compared to the first. So this is another one of those ratio questions. Here we have the normal equation. And now here's the new equation with the adjustments made. We've doubled the length, and we've 1/2 the cross-sectional area. Well, if that's the case, we have to do the same factors on the left side of the equation. So we're multiplying the resistance by 2 and then dividing it by 1/2, which is the same thing as multiplying it by 2 again. And then 2 times 2 makes a 4. So by affecting the length by 2 and the area by 1/2, we have multiplied the resistance of this wire by 4. So we are looking for choice 4 for question 45. Question 46 is, I guess, a variable resistance question in the sense that we are increasing the temperature of the filament of a light bulb. And this happens with incandescent lamps. This is why incandescent light bulbs are hot if you leave them on for more than 30 seconds. As temperature increases, resistance increases. And this is just something you're supposed to know. The analogy I'll give you is that the most familiar electronic appliance to you is your cell phone. So you know that when your phone is warm, whether you've been using it for a while or it's been sitting in the sun, and you try to swipe the screen or hit buttons on the touchscreen, sometimes it slows down if it's too warm. Temperature increases resistance. And by slowing down, I'm referring to the current. Back to Ohm's law. If voltage of your battery remains the same, which it will, and you're increasing resistance by increasing temperature, then you have to decrease the current for that equation to still hold steady. So those are the answer choices we're looking for. Resistance increases, current decreases. Choice 1 says those phrases. Question 47 is about diffraction. which is a wave property we did not focus on very much. We did mention it. The term is on your wave's term maps, but we didn't get too involved with it. This is just a definition of the concept of diffraction. Diffraction of a wave takes place when it encounters a barrier with either a gap or some kind of way for the wave to, swing through or wrap around that barrier. Diffraction takes place the most when wavelengths are short and the gap is very narrow. If I could finish this picture of these diffraction examples in the answer choices, let's say here's your gap and here's your incoming planar wave. This is what it would look like past the gap. It's almost like the wave starts as a spherical wave front past the gap, but this effect is made more intense if the wavelengths are shorter, meaning the waves are closer together, the wave fronts. Just something you're supposed to know for this question. There's no equation that shows that. So this is kind of a definition of diffraction in terms of a diagram. Question 46 mentions a singer making a glass vibrate at a certain wavelength at STP. You may remember the phrase STP from chemistry. It stands for standard temperature and pressure. The only place we see that phrase on our tables is in the context of the speed of sound on the first page, right here. So obviously we're dealing with a sound wave here if we're talking about someone singing. This is an example of resonance. If the glass is vibrating, even though we're not actually touching it, then the glass is vibrating at its natural frequency due to a wave being produced somewhere else that matches that frequency. Now, what is that frequency? That's what the question is. So we'll have to simply use the wave velocity equation, which is the first and the default equation for waves. Bring it down to that page right here. V equals F times lambda. As long as we're using all proper units, we can use the equation with no problem. It's like we've got 0.32 for our wavelength. The speed of sound, which we can go back and look up, is 331 meters per second. So this is just a simple plug it into the equation. 0.32 for wavelength, 331 for velocity. Frequency will be something around 100 meters per second. Just estimating it. Oh, I'm sorry, no, something around 1,000 meters per second because we're moving the decimal 3 times to make it, something around 1,000. You can use your calculator and find the exact answer, but choice 3 is what it should be. Number 49, a standing wave. You should be very familiar with these pictures. We've seen plenty of them by now. The question asks for maximum constructive interference. So realize these standing waves are thousands of wave pulses bouncing back and forth between the two endpoints and reflecting. And they're also interfering with all the other wave pulses in the system at the same time. But the pattern it's making is one where there's always constructive interference at these antinodes at points B and D, and there's always maximum destructive interference at the nodes. That's A, C, and E. So I just gave you the answer with that statement. Constructive interference at the antinodes, and those are locations B and D. So this question is asking us to understand what the nodes and antinodes look like, and also which ones correlate to the maximum interference pattern. So choice 3 is the choice we want here. And the final question on the practice exam is a circuit question. It's asking for the proper placement of a voltmeter to read across resistor 2 for its voltage. Voltmeters have to be placed in parallel to the section of the circuit you're interested in reading the voltage of. That's because a voltmeter has theoretically infinite resistance. For the voltmeter to read voltage, it cannot receive current into itself. The current carries voltage with it. So if you're allowing your circuit to deviate away from the resistor to go through the voltmeter with current, then the voltage won't be consumed in the resistor because you've snuck around it through the voltmeter. So The voltmeter only reads voltage. That means it's equal in parallel. So choices 1 and 4 do not have voltmeters in parallel. They cannot be the answer. Voltmeters will never be placed like that. Choice 2 has a voltmeter reading the voltage through the battery, or you can consider it the total voltage between the beginning of resistor 1 and the end of resistor 2. Imagine the current is looping around counterclockwise. Clockwise, going from this top junction through 1 through 2 back to here. The voltmeter arms are reading both voltages added together. That's not what we're looking for. We only want R2. That is what choice 3 shows us. Imagine the voltmeter like the ones you used in class with the red arm and the black arm wrapping around. You've got one needle before R2, one needle after R2. That'll tell you the voltage difference between a location before the resistor and after. That'll read you how much voltage was consumed in that resistor. So choice 3 is your answer. I hope these videos have helped you, clarify why the answers in the key are what they are. Good luck on your final exam. You guys are welcome to send me emails if you have questions over the weekend. I'll look at it every so often and answer you as quickly as I can. Good luck next week. I'll see you then. Bye-bye.